Imagine standing on a patch of ground in what is now the Yucatan Peninsula of Mexico, roughly 66 million years ago. The sky above you is clear, the air warm and humid, alive with the calls of creatures you would never recognize. Dinosaurs moving through dense forests, pterosaurs cutting arcs through the blue overhead, ancient marine reptiles gliding through the shallow inland seas nearby. Life on Earth is, by any measure, thriving. It is perhaps the most biologically rich and diverse moment the planet has ever known. And then, without any warning at all, something happens. A streak of light appears in the sky. At first, it might look like a shooting star, a brief, beautiful thread of brilliance against the daytime blue. But within seconds, that thread becomes something far more terrifying. It becomes a mountain. A mountain moving faster than any object has any right to move. A rock roughly the width of a major city. Some estimates say 12 kilometers, others push that number closer to 15, is hurtling through the atmosphere at approximately 20 kilometers per second. That is not a typo. 20 kilometers. Every single second. In the time it takes you to blink, it has moved more distance than most people travel in an entire commute. And before you can even process what you are seeing, before the sound can reach you, before the pressure wave hits, the world ends. Not metaphorically, not symbolically. It literally ends for something between 75 and 80% of all species alive on Earth at that moment. Now pause here, because before we go any further, there is something you need to understand. That rock, that city-sized, civilization-ending, world-altering projectile, was not some rare cosmic fluke. It was an asteroid. And the universe is absolutely full of them. There are hundreds of thousands of known asteroids in our solar system right now. Possibly millions more we have not yet discovered. Some of them are tiny, the size of pebbles. Some of them are massive, larger than the one that killed the dinosaurs. And some of them right now, tonight, as you are listening to this, are moving through space on paths that bring them uncomfortably close to Earth. So let's ask the obvious question. The one that should be sitting in the back of your mind already, making you just a little bit uneasy. How much do you actually know about asteroids? And more importantly, how much should you know? Because the story of asteroids is not just a story about ancient history or dinosaur extinction. It is a story about the formation of our entire solar system. It is a story about where water on Earth came from, about where the building blocks of life itself may have originated. It is a story about near misses that could have wiped out civilization and that most people have never even heard of. It is a story about scientists racing against time, governments arguing about funding, and the very real possibility that humanity is right now developing the tools it would need to prevent its own annihilation. And threaded through all of that, like a silver wire connecting every single one of these extraordinary moments, is one fundamental truth. Asteroids are not just relics of the past. They are the present. They are the future. They are, in a very real sense, the architects of everything you know. 30 facts. 30 windows into a world most people never think about. And by the time we are done, I guarantee you will never look up at a night sky the same way again. Let us begin. Picture the solar system as it was approximately 4.5 billion years ago. Not the clean, organized structure we think of today. The tidy orbital paths, the predictable seasons, the reassuring stability. No. What existed 4.5 billion years ago was chaos. Pure, magnificent, terrifying chaos. The sun had only recently formed, a blazing newborn star at the center of a vast spinning disk of gas and dust. And within that disk, particles were colliding, clumping together, growing, becoming something. This process is called accretion, and it is one of the most important and least appreciated processes in the history of the universe. Tiny grains of material, silicon, iron, carbon, oxygen, all sorts of elements forged in the hearts of stars that had lived and died long before our sun was born, began sticking together. First into pebbles, then into boulders, then into objects we would call planetesimals, the precursors of actual planets. Most of those planetesimals eventually got swept up into the 8 planets we know today. But not all of them. A vast number of them were left over. Orphaned fragments of the solar system's formation, scattered by gravitational forces, flung into distant orbits, left to drift. Those leftover fragments are what we now call asteroids. This is fact number 1, and it carries a weight that most people do not immediately appreciate. Asteroids are not invaders from outside the solar system. They are not cosmic debris that wandered in from somewhere else. They are original material, ancient beyond almost any human concept of time, from the very construction of the solar system itself. When you look at an asteroid, you are looking at the raw ingredients of planets. You are looking at what Earth looked like before it became Earth. You are, in a very literal sense, looking at your own origins. And here is where the first thought-provoking question enters. Ask yourself this: if asteroids are the original building blocks of the solar system, and Earth formed from those same building blocks, what does that mean about the relationship between asteroids and everything on this planet, including you? The answer, as we will discover, is far more intimate than you might expect. The largest concentration of asteroids in our solar system lives in a region between Mars and Jupiter called the main asteroid belt. When most people hear the phrase asteroid belt, they probably picture something from a science fiction movie, a dense, almost impassable field of spinning rocks that spaceships have to dodge at high speed. The reality is almost disappointingly different, and yet in its own way, far more interesting. The main asteroid belt is enormous. We are talking about a region that spans roughly 140 to 340 million miles from the Sun. It contains, by current estimates, somewhere between 1.1 and 1.9 million asteroids that are larger than 1 kilometer in diameter. There are also tens of millions of smaller ones. And yet, and this is fact number 2, if you took every single object in the main asteroid belt and compressed it all together, the total mass would be less than 4% of the mass of our own moon. The moon. The relatively modest rock that orbits Earth and drives the tides. The asteroid belt looks dramatic on paper, but in reality, the objects within it are so spread apart that if you were a spacecraft flying through it, you would be extraordinarily unlikely to hit anything. The average distance between objects in the asteroid belt is something like 600,000 miles. That is not a crowded highway. That is closer to an empty parking lot with a few stray shopping carts scattered across it. But do not let that diminish your sense of the scale involved here. Because even though those rocks are spread apart, even though the belt is mostly empty space, what it represents is staggering. It represents an entire planet that never formed. Jupiter's gravitational influence, that massive, domineering gas giant, was so powerful that it prevented the material in the belt from ever coalescing into a proper planet. Jupiter essentially broke up the party before it started. And so instead of a 9th planet between Mars and Jupiter, we got the asteroid belt. We got millions of fragments, frozen in time, preserved in space, waiting. Now here is something that should stop you in your tracks. Something that researchers and planetary scientists find deeply, almost philosophically interesting. Because the asteroid belt was not always where it is now. The outer solar system, in its early history, was a very different place. The giant planets, Jupiter, Saturn, Uranus, Neptune, were not always in the positions they currently occupy. There is a scientific model called the Nice model, named after the city of Nice in France where the researchers who developed it were based, and it describes a period of catastrophic instability in the early solar system, roughly 4 billion years ago, during which the giant planets migrated significantly in their orbits. Jupiter moved inward. Saturn moved outward. Neptune was flung far from its original position. And all of this orbital chaos sent a rain of asteroids and comets hurtling inward toward the inner solar system, toward the rocky planets, including Earth. This period is called the Late Heavy Bombardment, and while some scientists have recently debated how intense it actually was, many researchers believe it resulted in an extraordinary number of large impacts on the Moon and on Earth. The craters we see on the moon today, those pockmarks visible even to the naked eye, many of them date to this period. Earth would have experienced similar bombardment, but our geologically active planet has erased most of that evidence over the subsequent billions of years. Which brings us to a question that should feel almost vertigo-inducing if you let it sink in. What if the late heavy bombardment was not just a catastrophe? What if it was, paradoxically, a gift? Because here is fact number 3, and it is one that has genuinely reshaped how scientists think about the origins of life on Earth. Many researchers now believe that a significant portion of Earth's water, the oceans, the rivers, the rain, the water in every cell of your body, was delivered to our planet by asteroids and comets during the late heavy bombardment. This is not a fringe theory. It is a serious scientific hypothesis supported by growing evidence, including isotopic analyses of water found in asteroids that match the isotopic signature of Earth's oceans far more closely than previously thought. Think about what that means. The very substance that makes life possible on Earth, water, may have arrived here on the backs of the same kinds of rocks that later killed the dinosaurs. Life might owe its existence to asteroid impacts, and it might have been nearly snuffed out by them as well. The same cosmic mechanism that built the conditions for you to exist is also the mechanism that has come close to erasing everything multiple times. If that does not make your head swim a little, I am not sure what will. But let us come back to Earth, literally, and talk about what asteroids actually look like up close. Because for most of human history, asteroids were nothing more than points of light in the sky. Faint, barely visible objects that moved slowly against the backdrop of stars. The word asteroid itself was coined in 1802 by the astronomer William Herschel, the same man who discovered Uranus, and it comes from the Greek word meaning star-like. Because from Earth, that is all they looked like. Little stars. Wandering lights. We did not get our first close look at an asteroid until 1991, when the Galileo spacecraft flew past an asteroid called 951 Gaspra on its way to Jupiter. The images it returned were revelatory. Gaspra was not the smooth, spherical body that many people might have imagined. It was irregular, cratered, almost potato-shaped, with a surface that told the story of billions of years of collisions and battering. It was ancient and wounded and oddly beautiful, the way old things often are. Since then, we have visited many asteroids up close, and each one has surprised us. Because here is fact number 4, asteroids come in an extraordinary variety of types, and each type tells a different story about where it came from and what it is made of. The most common type is called a C-type asteroid, and the C stands for carbonaceous. These are dark, ancient objects that are among the oldest things in the solar system. They are rich in carbon and carbon compounds, and crucially, many of them contain hydrated minerals. Minerals that have water molecules locked within their crystal structure. This is part of the reason scientists are so interested in the idea that asteroids delivered water to Earth. C-type asteroids make up somewhere around 75% of all known asteroids, so when we talk about the asteroid belt, most of what we're talking about is dark, carbon-rich, water-bearing ancient rock. Then there are S-type asteroids, the S standing for silicaceous or stony. These are brighter objects, composed mainly of silicate minerals and metals like iron and nickel. They are less common than C-types but still abundant, making up perhaps 17% of known asteroids. The famous asteroid Eros, which NASA's Near Shoemaker spacecraft actually landed on in 2001. The first spacecraft ever to land on an asteroid was an S-type. It was shaped like a peanut or a misshapen potato, about 34 kilometers long and 11 kilometers wide, and it tumbled slowly through space like a sleeping giant. And then there are the M-types, the metallic asteroids. These are, in some ways, the most dramatic. M-type asteroids are believed to be the exposed metallic cores of ancient planetesimals that were shattered by catastrophic collisions billions of years ago. Imagine a protoplanet forming in the early solar system, large enough that its interior heats up through radioactive decay, melts, and differentiates, meaning the heavy metals sink to the center while the lighter rocky material forms a mantle and crust. Now imagine another object smashing into that protoplanet with enough force to obliterate the outer layers entirely, leaving only the naked iron-nickel core tumbling through space. That is what an M-type asteroid is. A planet's heart, exposed and alone. The most famous M-type asteroid, and this deserves its own moment of focus, is called 16 Psyche. It is located in the main asteroid belt and it is enormous, approximately 280 kilometers in diameter at its widest point. Scientists believe it may be composed almost entirely of iron and nickel, which means it could contain more iron than the entire human civilization has extracted from Earth in all of recorded history. The economic value of Psyche has been estimated at somewhere in the vicinity of $10 quintillion. That number, in case you are trying to process it, is 10 followed by 18 zeros. It is a number so large it is essentially meaningless in current economic terms. Economists have pointed out that if you were to somehow bring all that metal back to Earth, it would not make you the richest person alive. It would collapse the global iron market entirely. But as a target for future space mining operations, Psyche represents something extraordinary, which is why NASA launched a mission specifically to visit it. The Psyche spacecraft launched in October 2023 and is currently on its way to the asteroid, expected to arrive in 2029. It will spend approximately 26 months in orbit around Psyche, mapping its surface, studying its composition, and helping scientists understand what the cores of terrestrial planets, including our own Earth, might look like. Because here is the thing about Earth's core that most people forget. We cannot visit it. We cannot drill to it. It is over 6,000 kilometers below your feet right now, and it is so hot and under such extreme pressure that no material we have ever invented could survive there. But Psyche might be sitting right there in space, a naked planetary core, accessible and waiting to be studied. It might be the best proxy we will ever have for understanding what lies at the center of our own world. Fact number 5, and it should fill you with a certain specific kind of wonder. We may learn more about Earth's own interior by visiting an asteroid 370 million miles away than we have been able to learn in centuries of geology conducted on our own planet's surface. Now let us talk about something that brings asteroids considerably closer to home. Let us talk about near-Earth asteroids, the ones that cross Earth's orbital path, the ones that astronomers track obsessively, the ones that keep a small but dedicated community of planetary defense scientists awake at night. Near-Earth asteroids, or NEAs, are defined as asteroids whose orbits bring them within 1.3 astronomical units of the Sun, meaning they periodically get relatively close to Earth's neighborhood. As of the time this was written, there are over 33,000 known near-Earth asteroids. Over 33,000. Think about that number. 33,000 separate rocks, ranging in size from small enough to burn up in the atmosphere to large enough to end civilization, all moving through the inner solar system on paths that intersect or come close to Earth's own path. Of those 33,000 plus known near-Earth asteroids, roughly 2,300 have been classified as potentially hazardous asteroids, PHAs, in the jargon of planetary science. This classification means that the asteroid is both large enough, at least 140 meters in diameter, and close enough in its approach to Earth, within about 7.5 million kilometers, to be considered a potential threat. Now, here is something important to understand about all of these numbers, because the human brain is not naturally equipped to process them correctly. Astronomers are not tracking these asteroids because they expect any of them to hit Earth imminently. The vast majority of known potentially hazardous asteroids have orbits that have been calculated out decades or centuries into the future, and for most of them, the probability of impact is vanishingly small. The reason scientists track them is precisely so that they can tell us the probability is small, and also so that if they ever discover one that is not small, we have warning. And that warning time matters enormously, because this is fact number 6, and it is one of the most counterintuitive things about planetary defense. Given enough warning years, or preferably decades, humanity currently has, or is actively developing, the technological means to deflect an asteroid away from Earth. We have already proved this is possible. In September 2022, NASA deliberately crashed a spacecraft into an asteroid called Dimorphos and changed its orbit. Changed the orbit of an asteroid. It worked. We actually did this. And we will talk about it in much more detail shortly, because the story of how it happened is extraordinary. But first, let us spend some time with the history of asteroid discovery, because it is a story that begins with a mystery and ends with a revolution in how we see the solar system. The year is 1766. A German mathematician and astronomer named Johann Daniel Titius has noticed something peculiar about the distances of the known planets from the Sun. There seems to be a mathematical pattern, a simple sequence of numbers that, when processed through a specific formula, predicts the orbital distances of Mercury, Venus, Earth, Mars, Jupiter, and Saturn with remarkable accuracy. Titius shares this pattern with another German astronomer named Johann Bode, who promotes it widely. The pattern becomes known as the Titius-Bode law. But when you plug the formula in, something odd happens. Between Mars and Jupiter, the formula predicts a planet at a distance of approximately 2.8 astronomical units from the Sun. No planet existed there. At least, none that had been discovered. And so astronomers began to look. There had to be something there. The math said so. On the first night of the 19th century, January 1st, 1801, an Italian astronomer named Giuseppe Piazzi was working at the Palermo Astronomical Observatory in Sicily, methodically cataloging stars, when he noticed a point of light that was moving. Not stationary like a star. Moving. He tracked it over several nights and confirmed that it was indeed moving, that it was orbiting the Sun, and that it was located almost exactly where the Titius-Bode law had predicted a missing planet should be. He initially thought he might have found a comet, but it showed none of the diffuse, hazy characteristics of a comet. Whatever it was small, compact, and circling the Sun in a distinctly planet-like manner. Piazzi named his discovery Ceres, after the Roman goddess of grain and harvests who was also the patron goddess of Sicily. And for a while, the world believed that Piazzi had found the missing planet. But then something strange happened. Astronomers kept looking in that region of space, and they found more. In 1802, Heinrich Olbers found another object nearby and named it Pallas. Then Juno was found in 1804, Vesta in 1807. It became clear that there was not one missing planet, but rather an entire population of smaller bodies, none of them large enough to be called a proper planet in the way the others were. This is where William Herschel coined the term asteroid, star-like, to describe these new discoveries. And the name stuck, even if the understanding of what these objects truly were would take another 2 centuries to fully develop. Ceres, the first asteroid ever discovered, is now also classified as a dwarf planet, the only one located in the inner solar system. It is massive enough that its own gravity has pulled it into a roughly spherical shape, unlike most asteroids which are lumpy, irregular, and distinctly not spherical. At 940 kilometers in diameter, Ceres contains about a third of the total mass of the entire main asteroid belt. And when NASA's Dawn spacecraft entered orbit around it in 2015, it revealed something that astonished everyone. Mysterious bright spots on Ceres' surface, visible even from deep space, clustered in craters and shining against the dark terrain like lights in the night. Those bright spots turned out to be deposits of sodium carbonate and other salts, the remnants of briny water that had been pushed to the surface from below. Ceres, it turns out, has a subsurface reservoir of salty water, possibly a layer of brine that extends throughout much of the dwarf planet's interior. Ceres may, in some sense, be a water world, not like the ocean world of fiction, but a body with substantial water in its interior, which challenges every assumption about where water exists in the solar system and how it got there. Fact number 7. There may be more water in Ceres than in all of Earth's freshwater combined. When you consider that we spent centuries thinking of asteroids and dwarf planets as dry, barren, dead rocks, the discovery of a potentially vast water reservoir in Ceres is nothing short of revolutionary. And speaking of revolutionary discoveries, Let us talk about the moment in the early 2000s when the asteroid Itokawa became one of the most important rocks in the history of space exploration. Itokawa is a small near-Earth asteroid, only about 535 meters long, shaped something like a sea otter floating on its back, or if you are feeling less whimsical, like a lumpy peanut. But what Itokawa revealed about asteroid structure appended decades of assumption. Before the Japanese Hayabusa spacecraft arrived at Itokawa in 2005, most scientists assumed that small asteroids were probably solid rocks, chunks of material held together by their own structural integrity, the way a boulder is. Itokawa proved that assumption wrong in the most striking possible way. The spacecraft's instruments revealed that Itokawa is not a solid rock at all. It is a rubble pile, a loosely bound collection of smaller rocks and dust, held together only by the weak gravitational attraction of all those pieces for one another. It has the density of roughly half what you would expect from solid rock. There are huge empty spaces inside it, voids, gaps, the internal structure of a pile of gravel rather than a single stone. This is fact number 8, and it has profound implications for planetary defense. If you want to deflect an asteroid from a collision course with Earth and that asteroid is a solid rock, you can strike it with a spacecraft and push it off course, which is essentially what the DART mission did with Dimorphos, and we will get there. But if that asteroid is a rubble pile, things get considerably more complicated. A sudden impact might not deflect it smoothly. The kinetic force might simply cause the pile to absorb the energy and keep moving, or worse, break apart into multiple fragments that are now on slightly different but still dangerous trajectories. You do not deflect a rubble pile the same way you deflect a solid rock. You have to be much more careful, much more nuanced, much more strategic. And here's the question that should be sitting in your mind right now. How many of those 2,300 potentially hazardous asteroids are rubble piles? The honest answer is that we do not know for certain. But based on what we have learned from visiting several asteroids up close, Itokawa, Bennu, Ryugu, it appears that the rubble pile structure may be quite common among smaller asteroids. Which means the threat model for planetary defense is considerably more complicated than simply aim spacecraft at rock, problem solved. Hayabusa did something else historic at Itokawa, something that had never been done before and that required years of planning and extraordinary engineering ingenuity. It collected samples directly from the asteroid's surface and brought them back to Earth. In June 2010, a small capsule parachuted down into the Australian outback containing microscopic grains of material from Itokawa, the first samples ever returned from an asteroid to Earth. Analysis of those grains confirmed that Itokawa is an S-type asteroid and that its material matches a specific type of meteorite we have found on Earth, called LL chondrites, helping to confirm the connection between specific asteroid types and the meteorites that fall from the sky. Which brings us, naturally, to meteorites. Because meteorites are the way most people will ever have a physical connection to the asteroid world, even if they do not realize it. Meteorites are pieces of rock that survive the fiery journey through Earth's atmosphere and reach the ground intact, or at least partially intact. And they are far more common than most people realize. It is estimated that roughly 500 meteorites reach Earth's surface every year. Most of them fall in the ocean, or in unpopulated areas, and are never recovered. But the ones that are recovered are scientific treasures, windows into the early solar system, physical samples of material that formed 4.5 billion years ago, long before Earth even existed. Different types of meteorites correspond to different types of asteroids. Stony meteorites, the most common, come from the rocky outer layers of asteroids. Iron meteorites, heavy, dense, unmistakably metallic, come from the cores of differentiated asteroids that were shattered by collisions. And then there are carbonaceous chondrites, a type of stony meteorite that contains carbon compounds and hydrated minerals, and which represents some of the most scientifically valuable objects humanity has ever studied. Fact number 9. Some carbonaceous chondrite meteorites contain amino acids, the building blocks of proteins, the molecular machinery of life itself. These amino acids were not contamination from Earth. Analysis of freshly fallen meteorites and comparison of isotopic ratios confirms that these organic molecules formed in space, on or in asteroids, billions of years before life ever appeared on Earth. The molecules essential to life were being synthesized in the void of space long before any living thing existed to use them. Does this mean life was seeded on Earth by asteroids? We do not know for certain, but it is a genuine scientific hypothesis called panspermia, or more specifically in this context, exogenesis, the idea that the organic precursors of life, if not life itself, arrived on Earth from space. And while it remains a theory rather than established fact, the discovery of amino acids in meteorites means that the building blocks needed to assemble life were arriving on early Earth in enormous quantities during the late heavy bombardment, when asteroid impacts were far more frequent than they are today. Whatever role those impacts played in threatening the early development of life, they may simultaneously have been enriching the chemical soup from which life eventually emerged. The universe, it seems, loves irony. Now let us shift our perspective dramatically and talk about one of the most stunning and least appreciated aspects of the asteroid story: the role that Jupiter plays in everything. Because Jupiter is not just the largest planet in the solar system. Jupiter is, in a very real sense, the solar system's bouncer, its guardian, its chaos engine, and its occasional executioner. And the story of how Jupiter interacts with the asteroid belt, and with Earth's history, is one of the most dramatic narratives in planetary science. Jupiter's gravitational field is so immense, so far-reaching, so powerful that it fundamentally shapes the entire inner solar system. The main asteroid belt exists in the form it does partly because Jupiter's gravity creates regions where stable orbits are impossible. These are called Kirkwood gaps, named after the 19th century astronomer Daniel Kirkwood, who first noticed them. At these specific distances from the Sun, asteroids cannot maintain stable orbits because Jupiter's gravity repeatedly tugs at them in the same direction at the same point in each orbit, a phenomenon called orbital resonance, gradually nudging their orbits into increasingly eccentric shapes until eventually those objects are flung out of the belt entirely. Some of those flung objects go outward, away from the Sun. Many of them go inward, toward the rocky inner planets, toward Mars, toward Earth. This is one of the mechanisms by which near-Earth asteroids are continuously replenished. The main asteroid belt is not a static reservoir. It is constantly losing material through the Kirkwood gaps, through collisions, through the subtle pushing and pulling of gravitational forces, and some of that material inevitably ends up on trajectories that cross Earth's path. But here's where the Jupiter story gets genuinely complicated, because for a long time astronomers thought of Jupiter primarily as Earth's protector, the great vacuum cleaner of the solar system, sweeping up comets and asteroids before they could reach the inner planets. The evidence for this protective role was compelling. Jupiter has been observed capturing and destroying comets. In 1994, the comet Shoemaker-Levy 9 was captured by Jupiter's gravity, torn apart into over 20 fragments by tidal forces, and then crashed sequentially into Jupiter's atmosphere over the course of a week, leaving dark impact scars larger than Earth in Jupiter's cloud bands. If that comet had somehow reached Earth instead, the results would have been catastrophic. So yes, Jupiter protects us. But here is fact number 10, and it comes with a dose of cosmic humility. Jupiter also endangers us. The same gravitational forces that fling comets out of the outer solar system can also direct them inward, toward Earth, on paths that would not exist without Jupiter's influence. There is a category of comets called Jupiter family comets, which have been redirected from the outer Kuiper belt into the inner solar system specifically by gravitational interactions with Jupiter. And the ongoing gravitational stirring of the asteroid belt, the Kirkwood gaps, the orbital resonances, while it removes many objects from dangerous paths, also ensures a steady stream of potential impactors entering the inner solar system. The current scientific thinking is nuanced. Jupiter's net effect over the long history of the solar system may have been moderately protective for Earth, but it is not the clear-cut guardian angel of popular imagination. It is more like a chaotic neighbor whose activities sometimes help and sometimes harm, in a ratio that we have not fully worked out. And now, speaking of chaotic neighbors, it is time to talk about the event that fundamentally defines the public imagination of asteroids. the one that wiped out the dinosaurs. The one that happened 66 million years ago in what is now the Yucatan Peninsula. The one that created the Chicxulub crater, a scar in the Earth 80 to 145 miles across, buried now under the Gulf of Mexico and beneath limestone and sediment, invisible to the naked eye but undeniably present, undeniably real, and undeniably the result of one of the most violent events in the history of life on Earth. The story of how scientists figured out what happened at the end of the Cretaceous period is itself extraordinary, and it begins not in Mexico but in a geological formation in Italy, in a town called Gubbio, in the 1970s. A geologist named Walter Alvarez was studying the rock layers in a gorge near Gubbio when he noticed something strange. There was a thin layer of clay separating the limestone rocks of the Cretaceous period from the limestone rocks of the Paleogene period. The Cretaceous rocks contained the fossils of abundant marine life, tiny single-celled creatures called foraminifera. The Paleogene rocks contained far fewer and different species, and between them was this thin, humble-looking layer of reddish clay. Alvarez brought samples of this clay back to his father, Luis Alvarez, a Nobel Prize-winning physicist at the University of California, Berkeley. Together, they analyzed the clay's chemical composition, and what they found changed science forever. The clay layer was enriched with iridium, a rare metal on Earth's surface but common in meteorites and asteroids. The concentration of iridium in that layer was 30 times higher than normal. Something had deposited a vast quantity of asteroid material across the entire planet at exactly the moment when the dinosaurs disappeared. In 1980, Walter and Luis Alvarez, along with their colleagues Frank Acero and Helen Michel, published their hypothesis. A massive asteroid impact had caused the mass extinction at the end of the Cretaceous. This became known as the Alvarez hypothesis. It was not universally accepted immediately. In fact, it was initially quite controversial. Many paleontologists and geologists resisted the idea. The geological consensus at the time favored a more gradual explanation for mass extinctions. Perhaps massive volcanic eruptions, like those that had produced the Deccan Traps in what is now India, which were happening around the same time and which released enormous quantities of carbon dioxide and sulfur dioxide into the atmosphere. Or perhaps slow environmental changes over millions of years. But the iridium layer, the Alvarez layer, was found not just in Gubbio. It was found all over the world. In Denmark, in New Zealand, in Spain. Everywhere geologists looked in rocks dating to the precise boundary between the Cretaceous and the Paleogene, the KPG boundary, as it is called, formerly known as the KT boundary, they found this thin layer of iridium-enriched clay. Something truly global had happened. And then they found the crater. Or rather, they found evidence for where the crater had to be. In 1978, a geophysicist named Glenn Penfield was working for the Mexican oil company Pemex, analyzing aerial magnetic survey data over the Gulf of Mexico, when he noticed an unusual circular structure beneath the sediment and seafloor. He recognized that it might be an impact crater, but his results were not published in mainstream scientific literature for over a decade. It was not until the early 1990s, after the Alvarez team's hypothesis was already widely known, that researchers made the connection between Penfield's circular structure and the KPG boundary impact. Drilling samples confirmed it. The Chicxulub crater, named after a nearby town, was real, it was enormous, and it dated precisely to 66 million years ago. Fact number 11. The Chicxulub asteroid impact released energy equivalent to approximately 1 billion times the combined explosive power of the atomic bombs dropped on Hiroshima and Nagasaki. 1 billion times. The energy released in a few seconds of impact was so vast that it defies any meaningful comparison to human experience. The impact vaporized billions of tons of rock and sulfur-rich sediment, launching them into the upper atmosphere and even into space. The immediate blast radius was utterly lethal to anything within 1,000 miles. Earthquakes far larger than anything in recorded human history rippled through the Earth's crust. Tsunamis of almost incomprehensible scale, some estimates suggest wave heights of hundreds of meters, crashed across the surrounding ocean and coastlines. But the killing was only beginning. Because the most lethal effect of the Chicxulub impact was not the immediate blast. It was what came afterward. The vaporized material, the soot from wildfires ignited globally by falling ejecta re-entering the atmosphere as superheated particles, and the sulfuric acid aerosols from the vaporized sulfur-rich rocks. All of this created a global cloud that blocked sunlight for months, possibly years. Photosynthesis largely shut down. Plants died. The food chain collapsed from the bottom up. Animals that were too large to survive on whatever meager scraps remained, and most of the large animals fell into that category, went extinct. Not because they were burned or crushed in the impact, but because they starved to death in the long, dark, cold nuclear winter that followed. This is often called impact winter, and it is one of the most chilling concepts in all of natural history. The asteroid did not just kill what it hit. It killed the entire world's supply of sunlight, and in doing so, it killed the world. Approximately 75 to 80% of all species on Earth went extinct. The non-avian dinosaurs, the pterosaurs, the mosasaurs and plesiosaurs, the ammonites, countless species of plants, insects, and marine creatures. The world at the end of the Cretaceous period was rich and complex and extraordinary beyond anything most of us can fully imagine, and it was erased. Not slowly, not gradually, in geological terms, nearly instantly. But here is what you need to hold in your mind alongside that horror. Not everything died. Some things survived. And the survivors were, in many ways, the most important animals that have ever lived on this planet, because they were the ancestors of every mammal alive today, including you. At the time of the Chicxulub impact, mammals were small, generalist creatures, mostly no larger than a rat or a small cat, skulking in the shadows of the dinosaur-dominated world, active at night, eating seeds and insects and whatever else they could scrounge. For 165 million years, mammals had been exactly this. Small, marginalized, surviving but never thriving. The dinosaurs had ruled the large-body ecological niches for so long that mammals had barely had a chance to experiment with becoming larger. The asteroid changed that, overnight, in evolutionary terms. With the dinosaurs gone, with the ecological niches vacant, with new food sources emerging as the world slowly recovered from impact winter, mammals had, for the first time, a chance. They exploded. In the Paleogene period that followed the KPG extinction, mammals diversified with extraordinary speed. Within a geological blink of 10 million years, they had filled ecological niches across the world. Herbivores, carnivores, insectivores, omnivores, marine mammals, creatures that took to the air. The lineages that would eventually produce horses, elephants, whales, bats, and primates all trace their explosive diversification to the aftermath of the Chicxulub impact. Which means that the very fact of your existence, the fact that any human being has ever lived on this planet, may be directly attributable to an asteroid. Not because the asteroid delivered the building blocks of life or the water in the oceans, though it may have contributed to both of those, but because it cleared the board. It removed the dominant life forms that had been blocking the evolutionary path that eventually led to you. And now here's the question that should give you pause, the one I want you to sit with for a moment. If that asteroid had missed, if it had passed by Earth by even a small margin, or if it had hit at a different angle, or in a different location, or with a slightly smaller mass, would humans exist? The honest scientific answer is almost certainly not. The lineage of primates from which humans descended would not have had the ecological opportunity to develop. Something would exist. Life would have continued. The world would have recovered and diversified. But whatever intelligent life might have eventually emerged, it would not have been anything like us. It would have been something built from different evolutionary raw material, something that ran on a different branch of the tree of life. We are here because of the asteroid. We owe our existence, in a very fundamental sense, to 66 million years of consequences set in motion by a rock 12 to 15 kilometers wide. Now let us make a sharp turn from the deep past to the much more recent past, Because the history of humanity's encounters with asteroids and their smaller cousins does not end with the dinosaurs. Far from it. The Earth continues to be struck by extraterrestrial material constantly. Most of it is small, dust-sized particles and tiny pebbles that burn up harmlessly in the atmosphere. But occasionally, something bigger arrives. And when it does, the event can be stunning and terrifying in equal measure. On the morning of February 15, 2013, the residents of Chelyabinsk in central Russia got the most dramatic and terrifying reminder of this reality that anyone in modern times has experienced. At 9:20 in the morning local time, a rock roughly 20 meters in diameter, a relatively small asteroid by cosmic standards, smaller than a house, entered Earth's atmosphere moving at approximately 19 kilometers per second. In the course of less than 2 minutes, it screamed across the sky, leaving a trail of superheated plasma visible for hundreds of kilometers in every direction. Then it exploded. It did not hit the ground. It detonated in the atmosphere at an altitude of about 23 kilometers in what is called an airburst. The explosion released energy equivalent to approximately 30 times the power of the Hiroshima atomic bomb. The resulting shockwave, a pressure wave moving through the air at the speed of sound, then faster, hit the city of Chelyabinsk with enough force to shatter windows throughout an area of 7,000 square kilometers. Over 1,600 people were injured, most of them by flying glass. Nearly 3,000 buildings were damaged. Some people were knocked off their feet. A factory roof partially collapsed. Fortunately, because the object detonated high in the atmosphere rather than reaching the ground, there were no direct deaths from the impact itself, though hypothermia and injuries from broken glass kept emergency services busy for days. But the psychological impact was profound. People caught the entire event on their dashcam and security cameras. Russia's widespread dashcam culture meant that the Chelyabinsk event is the best documented asteroid impact in history, and the footage is both awe-inspiring and deeply unsettling. You can watch videos of that brilliant streak across the morning sky, followed by a flash brighter than the sun, followed by a shock wave that shakes the camera and shatters the glass. Here is fact number 12, and it should give you significant pause. The Chelyabinsk meteor was not detected before it arrived. None of the asteroid tracking programs in the world saw it coming. And this was not a failure of science or a gap in technology so much as it was a demonstration of a fundamental limitation. The Chelyabinsk object came from the direction of the sun. Our telescopes cannot effectively scan for incoming objects from the sunward direction because the sun's glare overwhelms them. It is as if you are trying to spot a car coming from the direction of a blindingly bright headlight. The car can be right there, and you simply cannot see it. This is exactly the kind of challenge that the next generation of planetary defense infrastructure is specifically designed to address. NASA's proposed NEO Surveyor Space Telescope, which would orbit the Sun between Earth and Venus and would be able to observe the sky from a vantage point that is not blinded by our own star, is designed partly to close this sunward blind spot. Because, as Chelyabinsk demonstrated, the objects we cannot see coming are the ones that most surprise us. And if you think 20 meters is too small to worry about, if you are thinking that a 20-meter rock causing broken windows is scary but not civilization-threatening, then I need to tell you about something that happened in 1908 over a remote region of Siberia called Tunguska. On the morning of June 30th, 1908, an object, almost certainly an asteroid or possibly a comet fragment, the exact nature is still debated, entered Earth's atmosphere and exploded at an altitude of somewhere between 5 and 10 kilometers above the Podkamenia-Tunguska River. The object itself is estimated to have been between 50 and 80 meters in diameter. The resulting explosion, another airburst, like Chelyabinsk but far more powerful, released energy equivalent to somewhere between 10 and 15 megatons of TNT. That is between 500 and 1,000 times the power of the Hiroshima atomic bomb. The explosion flattened approximately 2,150 square kilometers of Siberian forest. Roughly 80 million trees were knocked down, all of them pointing away from the explosion's epicenter like the spokes of a wheel. Reindeer herds within the affected area were annihilated. A man sitting on the porch of a trading post approximately 60 kilometers from the explosion was reportedly knocked off his chair by the shockwave. The explosion was heard hundreds of kilometers away. A seismic disturbance from the impact was recorded on instruments across the world. Fact number 13. If the Tunguska event had occurred over a major city rather than one of the most remote and uninhabited regions on Earth, the death toll would have been staggering. The object that caused the Tunguska event was not especially large by asteroid standards, 50 to 80 meters across. Objects of that size impact Earth roughly once every 1,000 years or so, statistically speaking. If one struck London, or Tokyo, or New York City, the resulting casualties could be in the millions. And here is the terrifying corollary to that fact. The Tunguska event was not discovered by the scientific community until years after it happened. Because it occurred in such a remote area of Siberia, news of it only reached the outside world slowly and imperfectly. The first scientific expedition to the Tunguska site did not arrive until 1927, 19 years after the event, led by a Russian mineralogist named Leonid Kulik. What he found when he got there was both spectacular and baffling. A vast area of flattened forest, trees stripped of their bark and branches, a landscape of devastation covering hundreds of kilometers. But no crater. The object had not hit the ground. It had exploded in the air, which is why there was no impact crater, and which confused researchers for decades. Even today, the Tunguska event remains somewhat mysterious. No fragments of the impacting body have ever been definitively identified, though some researchers have found microscopic traces of extraterrestrial material in sediment from peat bogs in the region. The exact composition and nature of the object. Was it an asteroid? A comet? A specific type of either? Continues to be debated. What is not debated is that it happened, that it was real, and that if it had arrived even a few hours later, when Earth's rotation had carried the populated regions of Russia to the position occupied by that remote Siberian forest, the results would have been unimaginably worse. Now let us talk about something that most people find genuinely surprising when they first learn about it. The extraordinary difficulty and complexity of actually finding asteroids before they find us. Because you might think that with all of modern astronomy's power, the giant telescopes, the space-based observatories, the computerized sky surveys, we would have a complete catalog of everything out there. We do not. Not even close. NASA and its partners have made enormous progress in cataloging near-Earth asteroids. In 2011, NASA achieved a goal of identifying 90% of all near-Earth asteroids larger than 1 kilometer in diameter, the civilization-ending class of objects. This was a significant achievement. Large objects are easier to spot because they are brighter, and the survey systems that have been built over the past 3 decades, including Linear, NEAT, Spacewatch, Catalina Sky Survey, and Pan-STARRS, have found tens of thousands of asteroids. The Catalina Sky Survey alone finds approximately 1,000 new near-Earth asteroids every year. But objects smaller than 1 kilometer are another matter. The current estimate is that there are somewhere between 15,000 and 20,000 near-Earth asteroids larger than 140 meters, the size range that could cause regional or even continental devastation. Of those, we have found and cataloged roughly 40%, which means roughly 60% of the regional devastation-sized objects in the near-Earth environment are still unknown to us. They are out there, moving through space, and we do not know their names or their orbits or how close they might come to Earth. This is fact number 14, and it should be both sobering and motivating. We are, in terms of planetary defense, still in the early stages of cataloging the threat. The good news is that the pace of discovery is accelerating. The Vera C. Rubin Observatory in Chile, when it comes fully online, is expected to dramatically accelerate the discovery of near-Earth objects. And the NEO Surveyor mission, if funded and launched as planned, will survey from space and could find the majority of the remaining unknown NEOs within its operational lifetime. But there is a catch. Finding an asteroid is only the first step. Once you find one, you need to track it long enough to determine its orbit with sufficient precision to say whether it poses a threat or not. A newly discovered asteroid might, on first observation, appear to have a disturbingly small probability of Earth impact. But as more observations are made and the orbital calculation is refined, the probability almost always drops dramatically, because most asteroids are simply not on impact trajectories. The scary headline of "newly discovered asteroid has 1 in 10 chance of hitting Earth" is almost never the final word. As observations accumulate, that probability almost always converges to nearly zero. Almost always, not always. Which brings us to the asteroid that currently holds the record for the highest impact probability ever calculated for a sizable object, and the object that triggered the creation of much of the modern planetary defense infrastructure we have today. Its name is Apophis. Apophis is an S-type near-Earth asteroid, roughly 370 meters in diameter. Its name comes from the Egyptian god of chaos, the Great Serpent of Darkness, which turned out to be an uncomfortably fitting choice. When Apophis was first discovered in June 2004 by astronomers Roy Tucker, David Tholen, and Fabrizio Bernardi at the Kitt Peak National Observatory in Arizona, initial orbital calculations were alarming. By late 2004, refined calculations suggested that Apophis had approximately a 2.7% probability of striking Earth in April 2029. 2.7% for a 370-meter asteroid. That is not zero. That is not even close to zero. In the world of planetary defense, where typical asteroid impact probabilities are measured in fractions of a percent, 2.7% is an emergency. The 2029 flyby was what made it so frightening. Apophis was going to pass extraordinarily close to Earth. Inside the ring of geostationary satellites, closer than some of our own orbiting spacecraft. And depending on the precise path it took through a narrow gravitational keyhole, a specific region of space where Earth's gravity would influence its orbit just enough to alter subsequent paths, it might be set on a course to strike Earth in 2036. The possible 2036 impact caused widespread public concern and significant scientific mobilization. Additional observations ultimately ruled out both the 2029 impact and the 2036 impact, and by 2021, NASA had eliminated Apophis from its list of impact risks for at least the next century. But the April 13, 2029 flyby, which will happen regardless, a close approach, not an impact, will still be one of the most extraordinary astronomical events in recorded human history. Apophis will pass so close to Earth that it will be visible to the naked eye. A faint but moving star visible across Europe, Africa, and Asia, moving across the sky over the course of several hours. Tens of millions of people will be able to step outside and watch an asteroid pass by with their own eyes. And multiple spacecraft missions are being planned to take advantage of this extraordinary opportunity. Because during that close approach, Earth's gravity will change Apophis's rotation and surface in ways that scientists are eager to study. The gravitational stresses of flying that close to Earth may cause surface material to shift or quake. It is a natural experiment that is simply not available in any other form. Fact number 15, and think about this one carefully. Apophis's 2029 flyby will bring a 370-meter asteroid, large enough to cause regional devastation if it ever did strike, closer to Earth's surface than our own geostationary communications satellites. The satellites that run your GPS, your weather forecasting, your satellite TV. An asteroid will pass through the realm of our own artificial infrastructure. It will not hit anything. The trajectory is well established. But the psychological and cultural significance of that moment, the moment when an asteroid becomes visible to the naked eye, when the cosmos literally intrudes into the everyday, is hard to overstate. Now let us take a step back from near misses and extinction events and explore some of the genuinely bizarre and wonderful science that asteroid research has revealed. Because asteroids are not just rocks. They are, in many ways, some of the strangest objects in the solar system. Take, for example, the phenomenon called the Yarkovsky effect. It sounds like something from a science fiction novel, but it is entirely real, and it is one of the most elegant and counterintuitive discoveries in solar system dynamics. The Yarkovsky effect is a tiny but real force that acts on asteroids, and on any rotating body in space, due to the uneven absorption and re-emission of solar radiation as heat. Here is how it works. An asteroid in space is warmed by sunlight on one side, the side facing the sun. As the asteroid rotates, the heated side turns away from the sun, but it does not instantly cool. It radiates that heat back into space as infrared radiation, but it does so slightly after the peak of heating, when the surface has rotated past the noon position. The asymmetry of this heat emission means that the asteroid is, very slightly, being pushed sideways by its own heat. It is as if the asteroid is powered by a tiny rocket engine made of warmth. Over short periods, this effect is completely negligible. But over thousands or millions of years, the Yarkovsky effect can shift an asteroid's orbit by significant amounts. It can push an object from a safe orbit into a hazardous one, or, theoretically, push it from a hazardous orbit into a safer one. And this has enormous implications for planetary defense, because if you want to predict where an asteroid will be in 50 or 100 years, you need to account for the Yarkovsky effect. And to do that, you need to know the asteroid's mass, its composition, its rotation rate, and its surface thermal properties, details that are difficult to determine remotely. The Yarkovsky effect was predicted theoretically and then eventually detected and measured directly. For the asteroid Bennu, which we will talk about shortly, the Yarkovsky effect has been measured with extraordinary precision, and it is one of the key sources of uncertainty in predicting Bennu's future orbit. Fact number 16. The Yarkovsky effect, a force produced by sunlight being absorbed and re-emitted as heat, may ultimately determine whether or not a given asteroid ever strikes Earth, on timescales of decades to centuries. A force that feels like it belongs in the realm of poetry and metaphor, the warmth of sunlight, gently pushing a mountain through the void, is actually one of the most important variables in planetary defense. Speaking of Bennu, let us spend some time with this remarkable asteroid, because Bennu has become, over the past decade, perhaps the most thoroughly studied small body in the solar system, and the story of NASA's OSIRIS-Rx mission is one of the great adventure stories of modern space exploration. Bennu is a near-Earth asteroid roughly 490 meters in diameter, slightly larger than the Empire State Building is tall, and it belongs to a category of asteroid that is thought to be among the most scientifically valuable. A B-type asteroid, a carbonaceous type that may contain some of the oldest and most primitive material in the solar system, including organic compounds and hydrated minerals. Bennu orbits the Sun every 436 days and comes close to Earth's neighborhood every 6 years. Its orbit has been calculated and projected far into the future, and the results are unsettling. Bennu has a cumulative probability of approximately 1 in 700 of striking Earth between 2178 and 2290. That probability sounds small, but for a 490-meter asteroid, it represents a significant concern. NASA launched the OSIRIS-Rx spacecraft toward Bennu in September 2016. It arrived at the asteroid in December 2018, and what it found there astonished even the scientists who had designed the mission. They had expected Bennu to have a relatively smooth surface, a sandy, beach-like terrain of fine-grained material where a sample collection device could gently touch down, press into the surface, and collect a sample. What they found instead was a surface littered with enormous boulders, some of them as large as a 10-story building. The terrain was nothing like what the modeling had predicted. Engineers had to completely redesign the sample collection plan on the fly, identifying a small, relatively clear area in a crater called Nightingale and programming the spacecraft to navigate to that specific spot with extraordinary precision. The touch-and-go sample collection event, executed on October 20, 2020, was one of the most tense and technically demanding moments in NASA history. The spacecraft descended to Bennu's surface, touched it for exactly 5.9 seconds, fired a burst of pressurized nitrogen gas to disturb surface material and kick it into a collection device, then backed away. Back on Earth, the signal telling mission controllers that the event had been executed would take 18.5 minutes to arrive. 18.5 minutes of dead silence while the spacecraft, on its own, executed the most delicate maneuver of its mission. When the confirmation arrived, and when cameras showed that the sample collector had been so effective that the mechanism had jammed open from the quantity of material collected, There were tears at the Mission Control Center in Tucson. They had touched an asteroid. They had collected its material. And they had done it without a single human hand within 330 million kilometers of the site. The OSIRIS-RX sample return capsule landed in the Utah desert in September 2023, containing approximately 121 grams of material from Bennu, the largest asteroid sample ever returned to Earth. When scientists opened the capsule and began analyzing the material, they discovered something extraordinary even before the detailed analysis began. The surface of the container was coated with dark, fine-grained material. And preliminary analysis confirmed that this material contained carbon, including carbon-bearing organic molecules, and hydrated clay minerals. Exactly the kind of material that might have carried the building blocks of life to early Earth. But perhaps the most stunning finding came when scientists discovered that the water content in Bennu's material matched the isotopic signature of Earth's water remarkably well. Here, in a sealed container in a laboratory, were pieces of an asteroid, pieces of ancient, primitive solar system material that seemed chemically connected to the very substance flowing through our rivers and filling our oceans and running through our veins. Fact number 17. The OSIRIS-RX sample from Bennu may be the most important scientific collection of the 21st century. Not because of what it tells us about this one asteroid, but because of what it suggests about the grand story of how Earth became the water-rich, life-bearing world it is today. Every gram of that material is a piece of the puzzle connecting the formation of the solar system to the emergence of life. Japan's asteroid sample return program has also made extraordinary contributions. The Hayabusa 2 spacecraft visited an asteroid called Ryugu, another carbonaceous asteroid, roughly 900 meters in diameter, and returned samples in December 2020. Analysis of those samples has been equally remarkable. Ryugu's material contains a diverse suite of organic compounds, including some of the most complex organic molecules ever found in extraterrestrial material. It contains amino acids, carboxylic acids, and other organic molecules that, on Earth, are associated with biological processes, though on Ryugu, they form through purely abiotic chemistry without any biology involved. Ryugu's material also contains something unexpected: uracil. Uracil is one of the 4 nucleobases found in RNA, ribonucleic acid, one of the 2 types of nucleic acid that carry genetic information in all known life on Earth. Finding uracil in an asteroid sample is one of the most arresting discoveries in astrobiology. It does not prove that life exists elsewhere in the universe. It does not prove that life was brought to Earth from space. But it means that at least one of the key molecular components of genetic information can and does form in the cold, dark void of space, in an asteroid, without any biological assistance. The raw materials of heredity exist in rocks tumbling through space. And here's the question I want you to sit with. If amino acids, nucleobases, water, and complex organic molecules can all form in asteroids and can all survive the violent journey of delivery to a planetary surface, what exactly is the gap between chemistry and life? How much of what we consider unique about life on Earth is actually the natural outcome of chemistry that begins in space? We do not know the answer yet. But asteroids are pushing us toward asking these questions with a rigor and a seriousness that would have seemed premature even a generation ago. Let us now talk about some of the most fascinating and genuinely strange asteroids in the solar system. The ones that break the rules, that challenge assumptions, that demonstrate just how weird and varied the asteroid world actually is. Start with the idea of a binary asteroid. Not all asteroids travel alone. A significant fraction of them, somewhere between 15 and 20% of near-Earth asteroids, turn out to be binary or multiple systems, meaning they have their own companions. A large primary body orbited by one or more smaller moonlets. This is more common than most people realize. The asteroid Didymos, for instance, is a large asteroid roughly 780 meters in diameter that has a small companion called Dimorphos, about 160 meters across, orbiting it at a distance of about 1.2 kilometers. Didymos and Dimorphos are the system that NASA's DART mission targeted in September 2022, and the fact that Dimorphos was a binary companion made it an ideal target. You could measure the change in its orbital period around Didymos precisely, without needing to know its exact distance from Earth moment to moment. Which brings us to the DART mission itself, because it deserves a detailed telling. DART stands for Double Asteroid Redirection Test, and it represents the first time in history that humanity deliberately and successfully altered the orbit of a natural body in the solar system. DART launched in November 2021 and spent approximately 10 months coasting through interplanetary space before arriving at the Didymos system. On September 26, 2022, at precisely 7:14 p.m. Eastern Daylight Time, the DART spacecraft, roughly the size of a small car, weighing about 610 kilograms, slammed into the surface of Dimorphos at approximately 6.1 kilometers per second. The collision was spectacular. The impact was visible from Earth-based telescopes as a sudden brightening of the Didymos system as enormous plumes of material were thrown out from the impact site. Hundreds of thousands of tons of dust and rock, creating a debris cloud that stretched for thousands of kilometers and was visible for weeks. Before the impact, Dimorphos completed one orbit around Didymos every 11 hours and 55 minutes. After the impact, that orbital period had changed. Scientists used ground-based observations to measure the new period with precision, and the result was stunning. The orbital period had been shortened by 33 minutes. DART had changed the orbit of Dimorphos by 33 minutes, a far larger change than the most optimistic predictions had estimated. The success of the DART mission was not just a technical triumph. It was a proof of concept that humanity can, given sufficient warning, deliberately alter the trajectory of an asteroid. We are not helpless. We are not the dinosaurs. We have options. Fact number 18. The most important number in the DART mission's results is not the 33 minutes of orbital change. It is the ejecta multiplier. The ejecta, the vast amount of material blasted off Dimorphos by the impact, actually contributed significantly more to the change in momentum than the impact itself. The spacecraft hit the asteroid, yes, but the explosion of material thrown outward from the impact site acted like a rocket exhaust in reverse, pushing Dimorphos even harder in the opposite direction. The ejecta multiplied the effectiveness of the impact by a factor of roughly 3.6, which means that when planning future planetary defense missions, scientists now know that the actual deflection from a kinetic impactor will be substantially larger than previously calculated, because the ejecta effect was even more powerful than models predicted. This is extraordinary news for planetary defense. It means we need less mass, less speed, and less energy than we thought to deflect a dangerous asteroid. It means the kinetic impactor technique, simply slamming a spacecraft into an asteroid, is more effective than the model suggested. It does not mean we can be complacent, but it does mean the universe has given us a slightly larger margin of safety than we realized. Now let us speculate for a moment, because the DART mission invites a fascinating thought experiment. We know kinetic impactors can work. We know we can change asteroid orbits. But what if we discovered an asteroid tomorrow, a large one, a kilometer or more in diameter, on a confirmed collision course with Earth? How much warning would we need? How would we respond? The planetary defense community has thought about this extensively, and the honest answer is, it depends enormously on how much warning time you have. With decades of warning, say 50 or 100 years, a relatively modest kinetic impactor could, applied early enough, push the asteroid's orbit just enough to ensure it misses Earth by a comfortable margin. The earlier you act, the less force you need, because even a tiny change in velocity, applied decades before the predicted impact, accumulates over time into a large change in position. This is the elegance of orbital mechanics. Small changes, early enough, can prevent enormous consequences. With less warning, say 10 years, you would need a larger, more powerful intervention. Multiple spacecraft, coordinated strikes, possibly a nuclear detonation in the vicinity of the asteroid to push it off course. And this is not science fiction. NASA has seriously studied nuclear deflection options as a last resort backup to kinetic impactors. The key distinction is that a nuclear device would not be used to destroy an asteroid. Blowing it up would simply create multiple fragments on roughly the same trajectory, many of which might still hit Earth. Instead, the nuclear option involves detonating the device near the asteroid to use the blast of radiation to heat and vaporize surface material, effectively creating a steam rocket from the asteroid's own material to push it off course. And with less than 5 years of warning, the situation becomes genuinely grim. The options narrow dramatically. There might not be enough time to mount an effective deflection campaign. Evacuation of the impact zone would be the primary response, which is feasible for smaller objects but essentially impossible for an impact area that could span a continent. This asymmetry of warning time is why early detection, finding hazardous asteroids as early as possible, is the single most important priority in planetary defense. Not technology, not nuclear weapons, not fancy deflection spacecraft. Detection. Knowing the asteroid is coming is 90% of the battle. Speaking of detection, let us talk about some of the technological systems that are currently operational and in development. The Catalina Sky Survey, based at the University of Arizona, uses 2 telescopes in Arizona and 1 in Australia to systematically scan the sky for moving objects. The Pan-STARRS survey at Haleakala Observatory in Hawaii uses a telescope with a massive field of view to take rapid, repeated images of large swaths of sky. The Atlas Survey Network covers the entire available sky every 2 nights. The Spacewatch program at Kitt Peak has been searching for near-Earth objects since 1980. Together, these ground-based surveys have discovered the vast majority of the 33,000-plus known near-Earth asteroids. But they have limitations. They struggle with objects coming from the sunward direction. They struggle with the faintest, smallest objects. They are limited by weather and by the fact that Earth's atmosphere blurs images in ways that space-based observatories are not subject to. This is why the upcoming generation of surveys is so important. The Vera C. Rubin Observatory in Chile, expected to begin full survey operations soon, will use a telescope with an enormous field of view and an exceptionally sensitive camera to image the entire southern sky repeatedly, discovering tens of thousands of new asteroids and refining orbits of known ones. The NEO Surveyor mission, if it launches as planned in 2026, will operate in space at a point in Earth's orbit where it can observe the sunward sky efficiently, closing the blind spot that left the Chelyabinsk meteor undetected. Fact number 19. The investment required to build and operate a comprehensive planetary defense detection system is relatively modest by the standards of other space expenditures. The entire NEO Surveyor mission costs roughly $1.5 billion. Less than some individual defense procurement programs, less than some film studio productions when you factor in marketing. For that investment, humanity gains years of warning before any sizable asteroid impact. The cost-benefit ratio of planetary defense detection is arguably the most favorable of any catastrophic risk mitigation program in existence. Now, let us make another dramatic shift and explore some of the more speculative and fascinating scientific theories about asteroids. Theories that push at the boundaries of what we know and invite us to think about the cosmos in new ways. One of the most intriguing is the idea that the solar system may have experienced a period of extreme planetary instability far more recently than previously thought. Not just the late heavy bombardment 4 billion years ago, but perhaps a second, more recent episode of gravitational chaos that sent a new wave of asteroids toward the inner solar system. Some researchers studying the cratering record on the Moon have proposed that there may have been a spike in large impacts around 800 million years ago, an event sometimes called the Chicxulub-type resurgence hypothesis, though it is speculative and contested. If such an event happened, it could have had significant effects on Earth's early animal life, perhaps even contributing to the long period of global glaciation sometimes called snowball Earth. This is speculative, emphasize the word speculative, but it illustrates something important. We do not fully understand the history of asteroid bombardment of Earth. The geological record is imperfect. Most ancient craters have been erased by erosion, by tectonic activity, by the grinding processes of geological time. We know the Chicxulub impact happened at exactly 66 million years ago, with precision measured in thousands of years, because the evidence is relatively recent and well preserved. But what happened before? What large impact struck Earth 200 million years ago? 400 million years ago? We do not have a complete picture, and the gaps in our knowledge are not reassuring. There are roughly 200 confirmed impact craters on Earth today. That sounds like a lot, but it is almost certainly a massive underestimate. The seafloor covers 70% of Earth's surface, and impact craters on the seafloor are extremely difficult to detect because the seafloor is constantly being renewed through plate tectonics. New material generated at mid-ocean ridges pushes the old seafloor down into the mantle at subduction zones, erasing the evidence. And on land, erosion, vegetation, and geological activity gradually erase even the most dramatic craters. The Vredefort crater in South Africa, the largest confirmed impact crater on Earth at roughly 300 kilometers in diameter, has been so heavily eroded over its 2 billion-year history that from the ground, you can barely tell it is a crater at all. You need satellite imagery or geological analysis to see the circular structure. How many Vredeforts have been completely erased? How many impacts of comparable or greater magnitude have happened in Earth's history that we simply have no direct evidence for? This is one of the great unanswered questions in planetary science, and the answer would reshape our understanding of how violent Earth's past has truly been. Fact number 20. The ocean floor may contain hundreds of undiscovered impact craters, some of them potentially enormous, whose existence we cannot currently detect because the evidence has been subducted into the Earth's mantle. The history of cosmic violence written into our planet's surface may be far more dramatic than anything we have yet been able to read. Now let us explore one of the most extraordinary and philosophically rich aspects of the asteroid story: the economic dimension. Because asteroids are not just scientific curiosities or planetary hazards. They are, potentially, the greatest source of natural resources ever available to humanity. And the space mining industry, once dismissed as science fiction, is becoming a serious area of investment and engineering. We have already talked about 16 Psyche and its staggering estimated value in iron and nickel. But the economic potential of asteroids goes well beyond iron. Rare metals, platinum group metals like platinum, palladium, rhodium, and iridium, are extraordinarily valuable on Earth because they are rare in the Earth's crust. But they are not rare in asteroids. Many metallic and even some stony asteroids contain significant concentrations of platinum group metals that, if brought back to Earth, would be worth trillions of dollars. The asteroid 1986 DA, for instance, has been estimated to contain something like 10,000 metric tons of platinum. At current market prices, that amount of platinum would be worth around $400 billion. And that is just one asteroid and just one metal. There are hundreds of thousands of asteroids in the main asteroid belt, and a significant fraction of near-Earth asteroids contain valuable metals. But the most economically valuable resource in the asteroid belt might not be any metal at all. It might be water. Water in space is extraordinarily valuable because it can be used to sustain human life, to grow food for long-duration missions, and most importantly, it can be split into hydrogen and oxygen through electrolysis, the two components of rocket propellant. An asteroid with abundant water effectively functions as a gas station in space. A ship that could refuel from asteroid water would not need to carry as much propellant from Earth's surface, reducing the mass, the cost, and the energy required for deep space missions dramatically. Water in space changes the economics of the entire solar system exploration enterprise. Several private companies have attempted to position themselves to take advantage of this potential. Planetary Resources, founded in 2012 by space entrepreneurs with backing from the aerospace industry, aimed to develop asteroid mining technology but was ultimately acquired and its asteroid mining program ended. Deep Space Industries had similar ambitions and a similar fate. The fundamental economic challenge is that the technology to extract, process, and transport resources from an asteroid does not yet exist at commercial scale, and the capital investment required to develop it is enormous. But this is changing. The emergence of commercial launch providers like SpaceX, which has dramatically reduced the cost of getting mass into orbit, means that the economics of space resource extraction are becoming progressively more favorable. And several governments have passed legislation explicitly recognizing the right of their citizens and companies to own resources extracted from space. The United States Space Act of 2015, and similar legislation in Luxembourg and elsewhere, established that while no country can claim sovereignty over celestial bodies, private entities can own the resources they extract from them. This legal framework is designed to incentivize investment in space resource extraction by providing legal certainty for investors. Whether it will succeed, whether asteroid mining will ever be commercially viable, is genuinely unknown. It remains a high-risk, long-horizon investment proposition. But the conversation has shifted from, is this theoretically possible, to, when will this become economically feasible? And that shift represents a fundamental change in how we think about the asteroid belt. Fact number 21. The asteroid belt contains enough iron, nickel, platinum, gold, and other valuable materials to provide every person currently alive on Earth with $1 trillion share of wealth, if it could be extracted and used without collapsing the markets for those materials, which is itself one of the central economic paradoxes of space resource extraction. The wealth is there. The challenge is accessing it and using it in ways that actually create value rather than simply flooding markets and eliminating the price premiums that make those materials valuable in the first place. There is also something deeply philosophical about the idea of asteroid mining that I think deserves a moment's attention. Asteroids, as we have established, are the original building blocks of the solar system. They are ancient beyond comprehension, unchanged since the dawn of planetary formation. Some of them carry within them the organic molecules that may have seeded life on Earth. They are, in a very real sense, sacred objects in the story of our origins. And yet, the practical benefits of asteroid resources, the potential to fuel a spacefaring civilization, to relieve pressure on Earth's own finite resources, to open the solar system to human habitation, are also real and potentially enormous. How do we balance scientific and cultural reverence for these ancient objects with the practical needs of an expanding civilization? This is a question that planetary scientists, ethicists, and space lawyers are genuinely grappling with. There are no easy answers. But the fact that we are asking the question at all represents a remarkable development in human thought. We are beginning to think of ourselves not just as inhabitants of Earth, but as potential citizens of the solar system. Let us shift now to talk about something that connects the outer solar system to the asteroid story in a way that most people do not expect: the Trojan asteroids. Jupiter does not just stir up the main asteroid belt from a distance. It also captures asteroids into its own orbital environment, in two groups that share Jupiter's orbit around the Sun. One group 60 degrees ahead of Jupiter and one group 60 degrees behind. These gravitationally stable regions, called Lagrange points, trap material that has accumulated over billions of years. The Trojan asteroids, Jupiter's Trojans, number in the hundreds of thousands, and they may be some of the most primitive and unaltered material in the solar system, preserved in their orbital niches since the very early solar system. But Jupiter is not the only planet with Trojans. Neptune has Trojans. Mars has Trojans. And, somewhat surprisingly, Earth has a Trojan too, a small asteroid discovered in 2010, called 2010 that shares Earth's orbit around the Sun, trapped in the leading Lagrange point 60 degrees ahead of us. It is small, roughly 300 meters, and its orbit is complex enough that it will not remain in its current stable configuration forever. But for now, Earth has its own companion in the same orbital path, a reminder that the solar system's gravitational architecture is far richer and more varied than the simple picture of planets in neat rings around the Sun. NASA launched a mission to visit Jupiter's Trojans called Lucy, named after the famous Australopithecus fossil that gave insights into human evolution. The idea being that Jupiter's Trojans are the fossils of the solar system's formation. Lucy launched in October 2021 and is scheduled to fly by one main belt asteroid and then visit 8 Trojan asteroids between 2025 and 2033. This would make Lucy the most flyby missions of any solar system body exploration in history. And what Lucy discovers may fundamentally reshape our understanding of how the solar system's outer regions were populated and how the giant planet migration event known from the NICE model played out. Fact number 22. Jupiter's Trojan asteroids outnumber the objects in the main asteroid belt at similar size ranges, and they may represent material from the very distant reaches of the early solar system, from the same region that is now occupied by the Kuiper belt objects beyond Neptune. If so, they are living links between the inner and outer solar system, preserved in their ancient orbits by Jupiter's gravitational embrace. Now let us talk about asteroid families, because asteroids, like people, come in families, and the story of those families is a story of ancient catastrophe recorded in rock. Many asteroids in the main belt are not random, independent objects scattered uniformly through space. They cluster in groups with similar orbits and similar compositions. And this is because they are the fragments of a single parent body that was shattered by a colossal collision at some point in the past. These are called asteroid families, and there are dozens of known ones. The Caronis family, the Vesta family, the Themis family, the Flora family. Each of these groups consists of hundreds or thousands of asteroids that were once part of a single, larger body. The parent body experienced a catastrophic collision with another asteroid, and the resulting debris, fragments large and small, spread through space while retaining the orbital characteristics of the original body. By studying the members of an asteroid family, you can essentially reconstruct the parent body, inferring its size, composition, and internal structure from the distribution and nature of the fragments. The Vesta family deserves special mention, because Vesta is one of the most fascinating objects in the main asteroid belt. At roughly 525 kilometers in diameter, Vesta is the second most massive object in the belt after Ceres, and it is the only asteroid large enough to have undergone differentiation, heating, melting, and separation into a core, mantle, and crust, and then survived largely intact. In other words, Vesta is effectively a frozen, incomplete planetary body. It has a south polar impact basin so enormous that if it were located on Earth, it would reach from the North Pole to the South Pole. The impact that created that basin threw enormous quantities of material off Vesta's surface, and some of that material eventually reached Earth as meteorites, a specific group of meteorites called HED meteorites, which we now know came from Vesta. We knew from meteorite analysis that HED meteorites had to come from a body that had undergone differentiation. But for a long time, we did not know which body. The Dawn spacecraft, which orbited Vesta in 2011 and 2012 before proceeding to Ceres, confirmed what isotopic and spectral analysis had long suggested. HED meteorites are pieces of Vesta. We have chunks of Vesta on Earth. You can hold them in your hand. And if you do, you are holding a piece of a body that is essentially a miniature, failed planet. A body that was building toward becoming a terrestrial planet before the solar system ran out of material and Jupiter's influence prevented further growth. Fact number 23. There are meteorites in museums and research collections around the world that are confirmed pieces of Vesta, a partially differentiated asteroid in the main belt. We have been able to study, in Earth's laboratories, material from a body that represents a failed attempt at planet formation. Vesta is, in some sense, Earth's little sibling that never grew up. Now let us shift perspective once more, because there is an aspect of the asteroid story that is fundamentally human in a way that all the orbital mechanics and spectroscopic analysis in the world cannot capture. It is the story of the people who search for asteroids. The scientists and amateur astronomers who spend nights in observatories, some of them world-class facilities, some of them backyard setups, scanning the sky for that one point of light that moves differently from the rest. Asteroid hunting is one of the few areas of professional astronomy where dedicated amateurs can still make real and significant discoveries. Many near-Earth asteroids have been found by amateur astronomers using small telescopes and sophisticated CCD cameras, applying the same patient and methodical scanning techniques used by professional survey programs. The International Astronomical Union maintains a formal process for crediting discoveries, and amateur-discovered asteroids are common enough that there is a vibrant community of asteroid hunters around the world. In Japan, in the United States, in Italy, in Slovakia, who have contributed thousands of discoveries to the catalog. There is something deeply moving about this. In an era when most of science has become so technical and expensive that ordinary individuals can barely participate, asteroid hunting remains a domain where a person with a decent telescope, a dark sky, patience, and passion can discover something that has never been seen before by human eyes. A rock that has been tumbling through space for 4.5 billion years, unseen and unnamed, and then one night, a retired engineer in his backyard in Arizona spots it and says, there is something new. The responsibility that comes with naming a newly discovered asteroid is also remarkable. Discoverers are given the right to propose a name for their asteroid, subject to approval by the IAU. Asteroids have been named after musicians, scientists, writers, athletes, philosophers, cities, and pets. There are asteroids named after Terry Pratchett and Frank Zappa and Freddie Mercury and Mr. Spock and Monty Python. The comedy troupe, not the snake, though presumably both would be honored. The asteroid 2309 is named Mr. Spock after the discoverer's cat, not the Star Trek character, which is a wonderful confusion that the scientific literature has had to navigate delicately. Asteroid 4148 is named McAuliffe after Krista McAuliffe, the teacher killed in the Challenger disaster. Asteroid 10419 is named Abramovic after the performance artist Marina Abramovic. The asteroid naming catalog is, in a strange way, a record of human culture, of the things and people that scientists and amateur astronomers found worth commemorating at the moment they made a discovery. It is a distributed monument to human civilization, written in the names of rocks tumbling through space. Fact number 24. There are asteroids named after all 7 of the Apollo 1 crew members who died in the 1967 fire, all 7 crew members of the Space Shuttle Challenger who died in 1986, and all 7 crew members of the Space Shuttle Columbia who died in 2003. The asteroid belt carries the names of people who gave their lives reaching for space. That strikes me as one of the most poignant and fitting tributes in all of human history. Now let us address something that combines all of these threads, the ancient and the modern, the scientific and the human, the fascinating and the frightening, and talk about the current state of planetary defense as a field and as a governmental and international priority. For most of human history, we had no concept of planetary defense because we had no awareness that there was a threat. The idea that rocks from space could strike Earth and cause catastrophic damage was not even widely accepted in the scientific community until the latter half of the 20th century. The Alvarez hypothesis was published in 1980, but even before that, the study of impact craters was only just beginning to mature as a scientific discipline. Eugene Shoemaker, the geologist and astronomer who is often called the father of astrogeology, and who did more than anyone else in the mid-20th century to establish that craters on Earth and the Moon were caused by impacts rather than by volcanic activity, spent years fighting scientific resistance to the idea. It is almost shocking in retrospect to realize how recently the scientific consensus shifted. Until the 1960s, many geologists and astronomers were skeptical that large meteorite impacts had played any significant role in Earth's geological or biological history. The dominant view was that Earth was largely shaped by slow, steady geological processes, volcanism, erosion, tectonics, and that impacts were curiosities, rare and minor in their effects. The Barringer meteor crater in Arizona, a perfectly preserved bowl-shaped hole in the Arizona desert, nearly 1.2 kilometers across and 170 meters deep, created about 50,000 years ago by an iron meteorite roughly 50 meters in diameter, was debated for decades as to whether it was an impact structure or a volcanic feature. Shoemaker's systematic work to understand impact cratering processes, combined with the Apollo missions to the Moon, which Shoemaker helped design the scientific protocols for, and the eventual confirmation of the Chicxulub crater, transformed the field. By the 1990s, the scientific community had fully embraced what is sometimes called the impact paradigm. The recognition that cosmic impacts have played a fundamental and recurring role in shaping Earth's surface and directing the evolution of life. With that recognition came the realization that the threat was ongoing. And with that realization came the first formal steps toward planetary defense. NASA created its Near-Earth Object Observations Program in 1998, charged with identifying and tracking potentially hazardous asteroids. The program has received steadily increasing funding over the years and now coordinates with international partners through the International Asteroid Warning Network, or IAWN, which connects asteroid tracking organizations around the world to share data and respond to potential threats. The United Nations has established the Space Mission Planning Advisory Group, or SMPAG, to coordinate international responses to potential asteroid threats. The Planetary Defense Coordination Office at NASA, established in 2016, is specifically responsible for directing the agency's planetary defense activities and coordinating with civil authorities, FEMA, and other governmental bodies. But here is a truth that planetary defense advocates will tell you, often with a mixture of frustration and gallows humor. The field remains chronically underfunded and underappreciated relative to the scale of the risk it is addressing. The entire annual budget for planetary defense at NASA, tracking, research, mission development, technology development, is a small fraction of what major sports teams spend on player salaries. For a program that is tasked with preventing a civilization-ending catastrophe, the resources are, by any reasonable assessment, inadequate. This is partly a psychological phenomenon. Humans are notoriously bad at allocating resources to low-probability, high-consequence risks, especially ones that seem abstract and distant. The probability that any individual alive today will experience a civilization-threatening asteroid impact during their lifetime is genuinely very low. But the probability that a sizable asteroid impact will occur at some point in the next several centuries, without warning, if we do not continue to develop detection and deflection capabilities, is considerably higher. And the consequences of being unprepared when it happens are so extreme that even a small annual investment in prevention is economically rational by almost any analysis. The asteroid that caused the Tunguska event, a 50-meter rock, hits Earth roughly once per millennium. A 100-meter rock like the one that might have devastated a major city hits roughly every 5,000 years. A 1-kilometer rock, capable of causing a regional catastrophe and global climate disruption, hits roughly once every few 100,000 years. And a Chicxulub-scale event, the kind that ends geological epochs, happens every 100 million years or so. These sound like comfortable timescales. But here is the thing. Asteroids do not follow a schedule. The probability is averaged over time, but the next impact could be tomorrow or it could be a million years from now. We have no way of knowing unless we look. And if we do not look, we will not see it coming. Fact number 25. The economic value of planetary defense detection programs, calculated in terms of risk reduction per dollar spent, is arguably the highest return on investment of any government program in existence. The cost of finding and cataloging near-Earth asteroids is tiny compared to the economic value of the catastrophes they prevent, even when those catastrophes are assigned relatively low annual probabilities. The math, done seriously, is compelling. And yet funding remains modest. Let us now turn to some of the most fascinating and unexpected connections between asteroids and other domains of human life, connections that most people have never considered. Consider the field of meteorology. When the Chelyabinsk meteor exploded in 2013, it generated infrasound, sound waves at frequencies too low for humans to hear, but detectable by specialized instruments. The explosion was recorded by infrasound monitoring stations all around the world, including stations designed to detect nuclear weapons tests under the Comprehensive Nuclear Test Ban Treaty. The same international monitoring system built to detect clandestine nuclear explosions detected the Chelyabinsk airburst from the other side of the planet. This is an extraordinary example of dual-use technology, infrastructure built for one purpose, arms control, providing crucial data for an entirely different application, understanding atmospheric impacts of extraterrestrial objects. Or consider archaeology. There are several ancient archaeological sites that may have been built at or near the locations of ancient impact events, possibly because our ancestors interpreted impact craters, impact glass, or meteorite falls as sacred or supernatural occurrences. The Abu Huraira site in Syria contains evidence of what some researchers interpret as a cosmic impact event around 12,800 years ago. Glassy material, microspherules, and nanodiamonds in an archaeological layer that suggests extreme heating. This period coincides roughly with the beginning of the Younger Dryas cooling event, and some researchers, in what is called the Younger Dryas impact hypothesis, propose that a fragmentary comet or asteroid impact may have contributed to or caused the Younger Dryas period and the extinction of the Pleistocene megafauna that occurred around the same time. This hypothesis is contentious. It is not accepted by most of the scientific community. The Younger Dryas has been attributed primarily to disruptions in ocean circulation patterns resulting from glacial meltwater pulses. But the impact hypothesis has not been definitively disproven, and some of the physical evidence, microspherules, magnetic grains, and shocked quartz found in the relevant archaeological layers at multiple sites around the world, continues to be studied and debated. The scientific community takes it seriously enough that it continues to be investigated, even if the majority currently leans against it. What makes this hypothesis particularly compelling as a story is its connection to one of the greatest mysteries in prehistoric archaeology: the apparent sudden collapse of the Clovis culture, one of the earliest human cultures in North America, around 12,800 years ago. The Clovis people, known for their distinctive stone tools and their hunting of large Ice Age mammals, disappear from the archaeological record at roughly the same time as the megafauna extinctions and the Younger Dryas cooling. Did a cosmic impact contribute to their demise? Did the collapse of the food web they depended on, as mammoths, mastodons, and other large prey animals went extinct, render their way of life impossible? We do not know for certain. But the question is real, and it illustrates how deeply the asteroid story intersects with human history even at its most ancient. Fact number 26. The oldest meteorite known to have fallen during recorded human history may be the Hoba meteorite of Namibia, which was found by a farmer plowing a field in 1920. It is the largest naturally occurring piece of iron known on Earth's surface, weighing approximately 60 tons and measuring roughly 2.7 by 2.7 meters. Nobody saw it fall, and no historical record of its fall has been found, suggesting it may have fallen thousands of years ago. But the most remarkable thing about the Hoba meteorite is that it has never been moved. Not even an inch. It is sitting in a field in Namibia exactly where it landed, and it is now a national monument. 60 tons of iron from the core of a shattered planetesimal, sitting in an African field, a visitor from the dawn of the solar system. Let us now explore something that pushes at the very edge of known science and ventures into genuine speculation, but fascinating, research-backed speculation. I want to talk about the possibility that the pattern of mass extinctions in Earth's history may be periodic. Not random, not scattered unpredictably through time, but periodic. In 1984, two paleontologists, David Ropp and Jack Sepkoski, published an analysis of the fossil record showing that mass extinctions appear to occur in a roughly regular cycle, approximately every 26 to 30 million years. If true, this periodicity would demand an explanation, because geological and biological processes generally do not produce such regular rhythms on such long timescales. Several astronomical explanations were proposed. The periodic passage of the solar system through the plane of the Milky Way galaxy, which happens roughly every 30 to 35 million years, might disturb comets in the outer Oort cloud, sending a shower of comets into the inner solar system. Or a hypothetical companion star to the Sun, nicknamed Nemesis, might periodically disturb the Oort cloud on its elliptical orbit. Or a large undiscovered planet in the outer solar system might do the same. The Nemesis hypothesis was serious enough that astronomers searched for it. They did not find it. The periodicity of mass extinctions itself has been debated, with many researchers arguing that the statistical evidence for it is not as strong as Ropp and Sepkoski claimed, or that the apparent pattern is an artifact of the imperfect fossil record. But the idea remains intriguing and has never been completely ruled out. The most recent analysis suggests that if there is periodicity in impact events, it may relate to the solar system's oscillation above and below the galactic plane as it orbits the center of the Milky Way, a motion that takes the solar system through regions of different density and potentially different numbers of disturbed Oort cloud objects. This hypothesis, while still speculative, has the advantage of relying on a known and confirmed process rather than an as-yet undetected companion star. This is speculation. Emphasize that. But it is grounded speculation. Speculation that has produced real scientific investigation and that is genuinely unresolved. And if the pattern of mass extinctions is in any sense periodic and in any sense connected to external cosmic influences, it would mean that the solar system's position in the Milky Way galaxy is not just an interesting astronomical fact, but a matter of existential importance for life on Earth. Our place in the galaxy would be our fate. Fact number 27. The gravitational influence of the Milky Way galaxy itself, the vast structure of hundreds of billions of stars within which our solar system is a single, insignificant point, may periodically disturb the distribution of comets and asteroids in the outer solar system, potentially contributing to cyclic variations in the rate of impacts on Earth. We live not just in a solar system but inside a galaxy, and the galaxy does not ignore us. Now let us talk about something that is rarely discussed in popular accounts of asteroids, but that is increasingly important in the scientific community. The role that space weathering plays in changing the surface properties of asteroids over time. When we study an asteroid remotely using spectroscopy, analyzing the light it reflects to determine what it is made of, we are not seeing its pristine, original composition. We are seeing a surface that has been bombarded for millions or billions of years by solar wind, a stream of charged particles from the sun, and by micrometeorites, tiny particles that constantly sandblast the surface and alter its chemical and physical properties. This process of space weathering changes the color and reflectivity of an asteroid's surface in ways that make it look different from its unweathered interior material. The surface of an S-type asteroid, space-weathered over billions of years, can look spectroscopically very different from the meteorites we find on Earth that come from S-type asteroids. Because when a meteorite falls through the atmosphere and reaches the ground, the weathering process is interrupted. The meteorite shows us what the fresh interior material looks like, while the asteroid surface shows us the weathered exterior. This created a long-standing mystery. Why did S-type asteroids, as observed spectroscopically from Earth, look different from the meteorites we believed came from them? The answer, confirmed by the Hayabusa mission to Itokawa, was space weathering. The fresh samples collected from just below Itokawa's surface and returned to Earth matched ordinary chondrite meteorites perfectly. The surface material was different. The mystery was solved, and in the process, we learned that reading an asteroid's composition from its surface reflectance is a more complicated exercise than previously assumed. This matters for planetary defense because knowing the composition of an asteroid, whether it is a loose rubble pile or a solid rock, whether it is rich in water or composed primarily of dry silicates, whether it has a metallic core or not, is important for planning how to deflect it. An asteroid that looks dark and featureless from Earth might be a carbon-rich, water-bearing C-type with a loose rubble pile structure. Or it might be something else entirely. The surface appearance can be misleading. You need to visit, or at minimum observe very carefully at multiple wavelengths, to know what you are actually dealing with. Fact number 28. The surface of almost every asteroid we have visited up close has surprised us. Each one has been different in some significant way from what we predicted. The asteroid world is not uniform, not simple, not easily generalized. It is as varied and complex as the geological world on Earth. And every new visit teaches us that we knew less than we thought. Let us now approach the end of our journey together by talking about the future of the human relationship with asteroids. Not just as threats to be avoided or resources to be exploited, but as destinations, as places. The long-term future of human civilization, if it is to be a truly spacefaring civilization, almost certainly involves humans living and working in and around the asteroid belt. Not on an asteroid in the way we think about living on Mars or the Moon. Most asteroids do not have enough gravity to hold a building to their surface, and anything you placed on the surface of a small asteroid could easily drift away if disturbed. Let us now explore something that pushes at the very edge of known science and ventures into genuine speculation, but fascinating, research-backed speculation. I want to talk about the possibility that the pattern of mass extinctions in Earth's history may be periodic. Not random, not scattered unpredictably through time, but periodic. In 1984, two paleontologists, David Ropp and Jack Sepkoski, published an analysis of the fossil record showing that mass extinctions appear to occur in a roughly regular cycle, approximately every 26 to 30 million years. If true, this periodicity would demand an explanation, because geological and biological processes generally do not produce such regular rhythms on such long timescales. Several astronomical explanations were proposed. The periodic passage of the solar system through the plane of the Milky Way galaxy, which happens roughly every 30 to 35 million years, might disturb comets in the outer Oort cloud, sending a shower of comets into the inner solar system. Or a hypothetical companion star to the Sun, nicknamed Nemesis, might periodically disturb the Oort cloud on its elliptical orbit. Or a large undiscovered planet in the outer solar system might do the same. The Nemesis hypothesis was serious enough that astronomers searched for it. They did not find it. The periodicity of mass extinctions itself has been debated, with many researchers arguing that the statistical evidence for it is not as strong as Ropp and Sepkoski claimed, or that the apparent pattern is an artifact of the imperfect fossil record. But the idea remains intriguing and has never been completely ruled out. The most recent analysis suggests that if there is periodicity in impact events, it may relate to the solar system's oscillation above and below the galactic plane as it orbits the center of the Milky Way, a motion that takes the solar system through regions of different density and potentially different numbers of disturbed Oort cloud objects. This hypothesis, while still speculative, has the advantage of relying on a known and confirmed process rather than an as-yet undetected companion star. This is speculation. Emphasize that. But it is grounded speculation. Speculation that has produced real scientific investigation and that is genuinely unresolved. And if the pattern of mass extinctions is in any sense periodic and in any sense connected to external cosmic influences, it would mean that the solar system's position in the Milky Way galaxy is not just an interesting astronomical fact but a matter of existential importance for life on Earth. Our place in the galaxy would be our fate. Fact number 27. The gravitational influence of the Milky Way galaxy itself, the vast structure of hundreds of billions of stars within which our solar system is a single, insignificant point, may periodically disturb the distribution of comets and asteroids in the outer solar system, potentially contributing to cyclic variations in the rate of impacts on Earth. We live not just in a solar system but inside a galaxy, and the galaxy does not ignore us. Now let us talk about something that is rarely discussed in popular accounts of asteroids, but that is increasingly important in the scientific community. The role that space weathering plays in changing the surface properties of asteroids over time. When we study an asteroid remotely using spectroscopy, analyzing the light it reflects to determine what it is made of, we are not seeing its pristine, original composition. We are seeing a surface that has been bombarded for millions or billions of years by solar wind, a stream of charged particles from the sun, and by micrometeorites, tiny particles that constantly sandblast the surface and alter its chemical and physical properties. This process of space weathering changes the color and reflectivity of an asteroid's surface in ways that make it look different from its unweathered interior material. The surface of an S-type asteroid, space-weathered over billions of years, can look spectroscopically very different from the meteorites we find on Earth that come from S-type asteroids, because when a meteorite falls through the atmosphere and reaches the ground, the weathering process is interrupted. The meteorite shows us what the fresh interior material looks like, while the asteroid surface shows us the weathered exterior. This created a long-standing mystery. Why did S-type asteroids, as observed spectroscopically from Earth, look different from the meteorites we believed came from them? The answer, confirmed by the Hayabusa mission to Itokawa, was space weathering. The fresh samples collected from just below Itokawa's surface and returned to Earth matched ordinary chondrite meteorites perfectly. The surface material was different. The mystery was solved, and in the process, we learned that reading an asteroid's composition from its surface reflectance is a more complicated exercise than previously assumed. This matters for planetary defense because knowing the composition of an asteroid, whether it is a loose rubble pile or a solid rock, whether it is rich in water or composed primarily of dry silicates, whether it has a metallic core or not, is important for planning how to deflect it. An asteroid that looks dark and featureless from Earth might be a carbon-rich, water-bearing C-type with a loose rubble pile structure. Or it might be something else entirely. The surface appearance can be misleading. You need to visit, or at minimum observe very carefully at multiple wavelengths, to know what you are actually dealing with. Fact number 28. The surface of almost every asteroid we have visited up close has surprised us. Each one has been different in some significant way from what we predicted. The asteroid world is not uniform, not simple, not easily generalized. It is as varied and complex as the geological world on Earth. And every new visit teaches us that we knew less than we thought. Let us now approach the end of our journey together by talking about the future of the human relationship with asteroids. Not just as threats to be avoided or resources to be exploited, but as destinations, as places. The long-term future of human civilization, if it is to be a truly spacefaring civilization, almost certainly involves humans living and working in and around the asteroid belt. Not on an asteroid in the way we think about living on Mars or the Moon. Most asteroids do not have enough gravity to hold a building to their surface, and anything you placed on the surface of a small asteroid could easily drift away if disturbed. Because here is the truth that every planetary scientist and every astronomer who works in this field knows in their bones. It is not a question of whether a dangerous asteroid will eventually be on a collision course with Earth. It is only a question of when. The solar system is old and active. The dynamics are real. The history of impacts is written in the craters of the Moon, in the iridium layer of the KPG boundary, in the flattened forests of Tunguska, in the broken windows of Chelyabinsk. The difference between us and every other species that has faced this threat is that we can see it coming. We can calculate trajectories. We can build spacecraft and send them to intercept incoming rocks. We can, if we choose to take this seriously, prevent the next mass extinction. Fact number 30. The total cost of the NASA DART mission, the first mission ever to successfully deflect an asteroid, was approximately $325 million. The budget of a single large Hollywood blockbuster. For less than the cost of making one movie, humanity proved that we have the capability to protect our planet from asteroid impacts. $325 million to change the orbit of an asteroid and prove that we are not helpless against the cosmos. If that does not fill you with something, wonder, or determination, or gratitude, or all three at once, then I have failed to tell the story properly. And I do not think I have failed, because this story tells itself. The asteroids tell it. They tell it in the water of our oceans and the carbon of our bodies and the craters on our moon. They tell it in the fossils of the dinosaurs and in the mammals that inherited the world the dinosaurs left behind. They tell it in the meteorites we find in the Sahara and the Antarctic ice and the Australian outback. They tell it in the Japanese spacecraft that returned samples from the most ancient and primitive rocks in the solar system. They tell it in the NASA mission that changed an asteroid's orbit and proved that intelligence is, at last, a meaningful factor in the evolution of the solar system. We started this journey standing on the Yucatan Peninsula 66 million years ago, watching the sky light up with the brightest and most terrible thing the world had ever seen. And we ended here, standing in the present, looking out at a solar system we are only beginning to understand, holding in our hands the samples of ancient asteroids, looking at the images returned by spacecraft we built and launched and guided to rocks hundreds of millions of miles away. Think about how far we have come. Think about how much further we need to go. Think about the fact that somewhere out there, right now, there are hundreds of thousands of asteroids we have not yet discovered, each one a piece of the solar system's 4.5 billion year history, some of them carrying the chemical signatures of life's origins, some of them on paths that could eventually bring them dangerously close to Earth. They are not our enemies. They are our ancestors. They are our threat. They are our future. They are the architects of everything we are and the potential destroyers of everything we have built. They are the most ancient and most consequential objects in our solar system, and most people will go their entire lives without ever truly thinking about them. But now you have thought about them, and I genuinely hope, that the next time you look up at the night sky and see a shooting star trace its brief, brilliant arc from horizon to horizon, you will feel not just the aesthetic pleasure of the moment, but the weight of what it means. That is not just light. That is material from the earliest moments of the solar system, burning up in the atmosphere, briefly visible, a reminder that the universe is not finished with us yet. That the cosmos does not forget the Earth, even when we forget the cosmos. And here is the question I want to leave you with. Not a question about science or about facts or about orbital mechanics. A deeper question. The one that, if you have been listening, you have probably already begun to form. Given everything we know about asteroids, given the role they played in building this world, in delivering water and organic molecules, in driving evolution by clearing the ecological board, in threatening civilization, in waiting out there right now in their hundreds of thousands. What does it mean to truly understand where we come from? And what are we going to do with that understanding? The story is not over. It is barely begun. And the next chapter is one we get to write ourselves, with the tools of science and the resources of civilization and the accumulated wisdom of everything the asteroids have taught us about the universe and about our place in it. The sky is not empty. The universe is not silent. And we are not alone in the cosmos, even if we have yet to find other minds within it. We share this solar system with the remnants of its own creation. We are made of those remnants. We are, in every meaningful sense, the universe's attempt to understand itself through the consciousness of a species smart enough to look up, smart enough to wonder, and, we can only hope, smart enough to act. That is the story of asteroids. That is the story of us.